microphone.
So, no, sorry. So today's elevator pitch is going to be from a very special team, building structures, and it's going to be done by Brian. I hope you enjoy it.
Okay.
Leave the floor to Brian, yeah?
Yeah. So very good. Thanks everybody. I hope you can hear me. I seem to be wired up very well. So today's, some of us would have seen a team last night that did quite well, but didn't quite get all the way, unfortunately. Today I'm here to speak about a team that does get all the way, the structures team. It's an elevator speech. Structures, people like tall buildings, and tall buildings have long elevators, so this is a long elevator speech. Right, so let me tell you about the structures team. The structures team is 70 people in the design side and 95 people on the supervision side. The design side is 50% in here in SAFE and 50% in Noida. We've got 3 design teams, and as of June this year we split the supervision team into an equivalent 3 teams as well. And so to get more coordination and more linkage between the teams. So the team leaders, who you probably all know, I hope you all know, Andy Veal has teamed up on the design side, teamed up with Ratnakar Amala for the supervision side. We've got Dave Murray for design, teamed up with Mohammed Hegassi for supervision, and Zahar Haddo with Aftab Alam. So those are the 3 teams. Charles Magro, who you should all know, is the overall leader for supervision, and Bob Scott is our technical guru, and Bob will be looking at technical aspects across all of the design and all of the supervision teams as well, although at the moment is pretty much full-time on One Zabeel. On top of that, we're hooked in quite closely to the global structures team. There's 2,500 structural engineers and technicians globally around the world. And we hook up into those via the Global Structures Leadership Team, the GSLT, and through that we can coordinate our chasing of clients and our relationships with clients, our technical sharing, our resource sharing, and we do reviews for each other as well sometimes. So what do we do? So I'm going to tell you a bit about what structural engineers do. You probably see them sitting here late at night and think, what are they doing? Okay, so if someone says to me, what does a structural engineer do? I say, we turn architects' dreams into reality. Actually, Andy Veal said that. And then the supervision team, we then ensure what we design gets built on site to the correct quality and also to the cost and program sometimes. So what is structural design? The first part of design is analysis, where we have to calculate the loads that the building will see and get those loads from the building down into the ground. 2 types of loads really, vertical and horizontal. The vertical loads are typically the weight of the building themselves plus the weight of whatever is inside the building, which is often people, but for car park structure it will be cars, for a shopping mall will be the shops and so forth. Typically the weight of the building is about 80% of the weight that we're carrying, so the building materials are very critical. So a 300-metre high tower, that's an 80-storey tower, will typically weigh about 120,000 tonnes if it's built out of concrete. And to put that into context, to build that, we'll have 5,000 concrete trucks delivering concrete to that building during the construction phase. We also have to sometimes design to avoid excessive floor vibrations, for example on hospitals where there's very high-tech equipment, and in particular in stadiums where we know that at some stage there's going to be a concert in the stadium. We're going to have thousands, probably tens of thousands of people all jumping into rhythm and putting that building into a vibration mode. So vibration of floors is very important. So we design the structural elements to carry the load from wherever the load is down to the ground level. Stiffer elements attract more load in the same way that a bigger pipe will carry more water. And so we can play with the stiffness of various elements by playing with the amount of the strength of the concrete or the thickness of the steel, the amount of reinforcement, and of course the size of the column or the wall. Due to the vast quantities of material required for building, costs dictates really only 2 materials that we can use, reinforced concrete or structural steel. And in the Middle East, reinforced concrete is more prevalent, and that's because reinforced concrete actually is quite labour intensive, but labour is quite cheap in the Middle East, so therefore we get concrete dominates. We also work with glass, timber, carbon fibre, and who knows, one day maybe that 80% of load that is the building itself will reduce massively because we'll have new materials such as carbon fibre or something like that one day, future ready. Then there's the horizontal loads, wind and earthquakes. Wind load in Dubai governs because we have quite high wind loads we have to design for, and so for high rise certainly wind will govern, and for low rise then seismic governs. We design for 160 kilometre an hour winds in Dubai. and obviously they make the building sway somewhat. The building sway we have to limit to 1/500 of their height. That means an 80-story building, which is 300 metres high will sway about 600 millimetres in a strong wind. The acceleration is limited, the sway is limited not by people, believe it or not, but by things like the lift shaft guide rails and the cladding tolerances. So we can't have the building bending too much, otherwise those things would not work. What determines people is the acceleration, and that's as the building stops one way and swings back the other way. And people can detect accelerations of greater than 15 milli-Gs per second, 15 milli-Gs, and that's the limit we designed for. On really windy days, if you're at the top of a tall tower and as the wind approaches the design ends, you might feel some movement on buildings. Certainly on non-occupied buildings, such as the spike at the top of the Burj Khalifa, where we put that base jump platform a few years ago. That's not designed for human occupancy because there's no humans up there, and you can really feel the movement up there, even on averagely windy days. And then we design for earthquakes. Earthquakes is different. We don't design earthquakes so that you can't feel the vibration. In fact, we all know when there's an earthquake, you definitely can feel the vibration. What we design seismically is to prevent collapse and prevent major damage. Here in Dubai, the earthquake that we designed for again is quite a high earthquake load, and it's expected to occur once in every 2,475 years, which is pretty unlikely, but it could be tomorrow, of course, that's the issue. So you will feel earthquake tremors in a building, but you can, if it's been designed by us and designed properly, you know it'll be safe. We must avoid resonance. I don't know if any of you have seen the video of the Tacoma Narrow Suspension Bridge. It's part of every structural engineer's course. It's a bridge that was designed in the States many years ago, and it was designed so that the wind-induced flutter of the bridge matched the building frequency, and it just swayed and swayed and swayed, and the amplitude got bigger and bigger until the whole thing collapsed. Obviously, we need to avoid those resonance issues, and we have to play, and we can play with the frequency of our buildings by playing with the mass and the stiffness of the elements. So we actually tune the building so that so we get the frequency we want. If we can't get the correct frequency just by playing with the members in the building, then we can use tune mass dampers. Here in Dubai, we've not needed, I think I'm right in saying we've not needed to use one yet. We've always managed to bring the frequency correct by using the building's own members. So once we get the work down to the ground, the load down to the ground, we hand it over to our geotechnical team. In fact, we don't hand it over because we work closely with our geotechnical team to get the loads then into the piles and into the foundations and into the ground. So that's how we do the analysis. Then we move to detailing. Once we know what size members we need and what stiffness we need, we have to detail it all up. For this, we follow codes. Typically in the UAE, it's now American codes, although RTA still use European British standards, Qatar still on BSEN. So there's various codes we use. And we model it all in 3D now. All of our projects now in 3D in Revit. And if you haven't seen the 3D room, which Jerry's set up, do try and get into that 3D room, because there's you put the goggles on and you can walk around the buildings. It looks really impressive. It's a great tool for seeing what we're really doing. Architects like it because they can really visualize what their building is going to look like. Clients like it, but it's also a very good tool for us to detect clashes with building services structures and architect structures. So it's a very practical tool as well as being really quite impressive. And then of course we've got to get all this to the guy on site, and let's face it, the guy on site is going to be hanging off the side of a scaffolding 45 degrees in a dusty climate. He needs something that's very simple and very easy to understand. So we put all this onto drawings. Typically for a tower we'll have several hundred drawings. For the One to Build project, for example, we've got about 600 structural design drawings, and they are given to the contractor so that he can start to produce his shop drawings. And his shop drawings are how he's going to actually build what we've told him to build. And on One to Build, for example, we are going to get thousands of drawings, maybe up to 10,000 shop drawings will come back in from the contractor. We need to review, our site team reviews and checks those and sends them back. That's why Binson's so busy over at One to Build. Throughout all of this, of course, we're coordinating with all the other discipline structures, with building services, with the architects and with all the other services. There's 3 levels of approvals. We do our own internal checks, and as I say, we do that between our 2 teams, or sometimes we'll send it internationally to one of our international offices to do a review. We then take it to the independent reviewer, who is an independent company that the municipality insists on, and then the municipality themselves do a check. So by the time our job gets to site, it's been pretty thoroughly checked. It can be painful, it can take many meetings and sometimes many months, but it's good because it means we know when that job gets to site we've got a very safe job. So now we're on site. Now the supervision team kicks in. It's where the real work starts, you could say, where concrete starts getting poured, steel starts getting put up. The site team have 2 roles really. Technical is the first one, so they have to ensure that what we've designed on the drawings is what gets built on site and ensure the quality of the construction is suitable. For this, we review the shop drawings, which I mentioned before, of which there's many thousands. All the material submissions that come in, we review that they're using the right materials, the right items that we've asked for. We look at all the deliveries coming in. We look at design changes that the contractor might ask for, or things we might have missed. And we've had a push lately to get a lot of our designers onto site. We're trying to blend this site and design teams. We've now got about half a dozen of our designers on site, and that's working very well. We look at how the formwork is prepared. We monitor the concrete placement. Concrete placement is usually done on night shift, especially in the summer, because the temperature is too hot for placing concrete during the day. So many of our site teams are working night shifts. Whenever we have a function in the evening, a lot of the guys come down, it's actually their breakfast, and they go on to work after our function in the evening. And of course, throughout all of that, we have massive coordination. So that's the technical side of supervision. We're also sometimes asked to do the construction administration. What is that? That's where we, as well as looking at the technical quality of what's going on the site, we also manage the contractor's program and his cost. This means that we look at his claims, we look at his variations that are coming in, and that means we put a resident engineer on the site who is, as well as being a good technical structural engineer, also has commercial and contractual and management skills, and he will manage the contractor as well as the team on site. And that RE will often continue to manage the site team after the structure is topped out, just because it gets so embedded into the contract, and he'll see it through to the end. There you go, that's the end of my long elevator pitch, because we like tall buildings. Thank you very much. Hopefully that gives you a bit more understanding of what structures do.